Now that you're familiar with confidence intervals for proportions, we want to talk about how to determine the sample size that's necessary, little n, in order to construct a specific margin of error. So researchers often know what they want their margin of error to be before they even go out and do a study. And because they want their margin of error to say be within like 2 percentage points, they want to figure out how many people are we going to have to seek out in order to answer this question accurately. One of the unique problems about proportions is that the standard error, and even the margin of error, they use the estimate itself to create the standard deviation. This is a problem because if we haven't actually gone out and done the survey, we don't know what p hat is. And so trying to work backwards from this margin of error formula, setting it equal to, again, say 2%, if we don't know p hat yet because we haven't done the study, we're not really going to be sure how to calculate n because we'll have multiple variables. There are two ways that we can work around this problem. One way is that we can use an estimate of p hat from a similar study or a preliminary study, or just if we kind of have a hunch about what we think the p hat value is going to be after we conduct a study. That's not as scientific as using a safer estimate of 0.5, and I'll show you in a minute why that's considered a safe estimate. So if ever you're not sure really what to do in this situation, I'm going to ask you to always default to using 0.5 as a p hat or a p-value in these calculations. Then, of course, you're already going to have a z-star value because you're going to have a confidence level suggested to you. If you don't, you're still going to use 95%, as I had said for means. You'll be given a margin of error to set equal to, or less than or equal to, greater than or equal to, and so then n will be the only variable that we need to solve for. Vocabulary-wise, sometimes using a p hat from a previous study is called like using a guessed p. P star equal to 0.5, using that value in our standard error formula is called a conservative estimate. So if you see directions that say use a conservative estimate, then I want you to use 0.5 as well. So this lends itself to the question, why do we use 0.5? Why is that the p hat value or the p star value that's going to give us a conservative estimate and not something else? Just by looking at some examples, I want you to think about what would happen if we had 0.25 that we used for p. When we calculate p times 1 minus p, so basically the numerator in our standard error formula, 0.25 times 0.75 is 0.1875. So that's going to give us, again, the numerator of our standard error formula. For 0.4, if we use that instead, we start to increase the value that we use. 0.4 times 0.6 is 0.24. 0.5, and this is the value that we are going to end up using, defaulting to, will give us 0.25. Even going just over 0.5 to 0.51, multiplying that by 0.49, that'll give us something slightly smaller than 0.25. And lastly, 90%, once we multiply that by 10%, that'll give us a rather small numerator for our standard error formula. So again, since p times 1 minus p is in the numerator of the standard error, increasing the numerator is going to increase the standard error, and thus it will increase the margin of error. By increasing them, we're giving that overestimate, and so we're going to be in the safe zone. Even if our p hat value ends up being smaller, that just means that our confidence interval will have an even narrower margin of error than we first intended to get, and that's good. We've talked about how the narrower the interval, the more precise our estimate is. For you calculus nerds out there, to give you a bit of a better explanation as to why 0.5 is the conservative estimate, why that's going to give us the highest value for our margin of error or for our standard error, I want you to think about the function where I'm just replacing x instead of p. If I were to distribute the x, I would get x minus x squared. I know that that's going to look like a parabola that faces down like a frown because of the leading coefficient of x squared. If I take the derivative of that formula, and even you students who have taken just pre-calculus, you did learn, believe it or not, how to find the derivative. If we take the derivative and then we set that derivative equal to 0 to find the maximum value, when we solve for x, we'll get 0.5. And so we know that an x value of 0.5 is going to maximize our result. And so that's going to give us the largest possible value of x times 1 minus x, again, making 0.5 the largest numerator and thus the conservative approach to determining a sample size from or for a proportion problem. You have another example to look at following this video that again is posted on Moodle. It will go through both using a guessed value for p-hat as well as using the conservative approach, and it'll just show you how those two numbers differ. In some problems that you come across, they will differ greatly, in others they won't. And when statisticians actually make the decision as to what they're going to use in terms of a sample size, that often depends on the implications of the study and what they're going to be using the results for.